enough. Welcome everyone to today's study group. Today we will be reviewing lecture 4. Thanks to Prashant who hosted the previous two meetups, and I think that in the last week he walked you through assignment 2. So today we'll be continuing with the next lecture, which is lecture 4. And so if anyone has any questions or if you want to add something, please feel free to join. So the lecture 4 is mostly about the math behind the feed forward phase and the back propagation. So I was okay. I'll be putting everyone on mute for now. So if anyone wants to say something, please unmute yourself. Yeah, so since this lecture is mostly about the math behind back propagation and feed forward phase, the partial derivatives and all that, I tried to find few resources which would help in better understanding the math behind all those things. I did go through a few blogs, but I found one which was very useful. I'll be walking through that blog once we are done with the slides. So this is in continuation with lecture 4. Here, this is about how the chain rule is applied for calculating the gradients for different components in the neural network. Here we can see that we start with the input x, and then what we have is we are going to take the weighted input. Wx is nothing but the x is our input, and W is the weight matrix. What's happening here is that instead of taking the input features or the input vector as is, we are going to take a weighted. We're going to take the weighted inputs, and then we're going to add bias to that. So that's what we're going to have in Z. And then in the next phase, we have the activation function, where the weighted input and the bias are passed through an activation function, and the output of that is going to be H. The purpose of the activation function is to add nonlinearity to the model, and we'll be discussing more about that soon. So I'm going to skip some of the parts here as we're going to discuss these things in detail in the blog. As we can see here, we have our input, which is kind of like 3 features, x1, x2, x3, and we have 2 neurons in the hidden layer. We only have one hidden layer here, H1 and H2. What's happening here is that each input feature is being passed to the hidden neurons. H1 is receiving the inputs from all the 3 input neurons. X1, X2, X3 has connections to H1. Similarly, H2 also has connections from all of the 3 input neurons. And what we have here is W23 denotes the weight of the weight for the connection between X3 and H2. So the first number denotes the neuron, the hidden layer neuron, and the second number represents the input layer neuron. So that's how the indexing is done here. And every hidden neuron comes with its own bias. So this you can think of, this is kind of the standard procedure, whether it's for images or whether it's for word vectors. The underlying process is going to be the same. It's just the structure is going to differ depending on whether the data is image or data is words, but the rest of the things are going to remain the same. So here are some tips about when calculating derivatives. So you must be familiar with chain rule by now. So this is the equation for that. So there is a more intuitive way of understanding chain rule, which we'll see in the blog. So we will get back to these things once we go through the blog. So let's say this is another example. This is one example where in the lecture it is discussed whether we should retrain the word vectors or not, and when should we retrain and when should we go with the pre-trained model itself. So here, as we can see, this is an example case in which the training data has the words TV and tele, and the word television is not present in the training data, but it is present in the test data. Yet, using the pre-trained word vectors, we see that all the three words are grouped together in the same region. They are rightly classified, or they are rightly analyzed here. We see all of them falling in the same region, which is good. So now let's say that you have some data of yours and you wanted to fine tune the pre-trained model, or you wanted to train your own model on using your own data. So there's a chance that once you retrain your model, the words might get rearranged in a way like this, where TV and tele are still in the same region and in the right region, whereas television is still there, it's not moved. And that's because what happened here is that TV and tele are in the training data. So when you're retraining, as per the new data, they are these words are reshuffled or rearranged, whereas the word television, since it's there in the test data, it's still there in the same place. So which is why so retraining the existing word vectors here is causing some sort of problem. And so what should we do, and how should we decide whether we should fine tune or not? So the first question is about should we go with pre-trained word vectors? So the answer is yes, because when we are talking about pre-trained word vectors like word2vec or any other publicly available pre-trained word vectors, they're actually trained on a huge data corpus with millions of words. So unless we have a data which is that huge, I think we can still stick to the pre-trained word vectors. So coming to the fine tune, when should we actually fine tune? So the more the rule is that if you have a small training data set in the lecture, it's discussed that a small here indicates anything like 100,000 to 2,000 words. 100,000 to 200,000 words can be considered as a small training data. So when you have much larger data set, then you can go for fine tuning and updating your word vectors. So backpropagation is a very critical part in a neural network flow. Like that's actually where you actually update your weights, which are randomly initialized in the beginning. So the way, though backpropagation can be done in different ways, the way you handle it can make a lot of difference computationally. So in the lecture, it's again discussed how how to do the backpropagation. Here, this is one example where, again, just reiterating what we discussed in the beginning, X is the input, and what's happening here is that is being multiplied with the weights. This can be called this is called different. This is called in different ways. One is you can call it as the net input, or you can also call it the inputs being scaled because they're being multiplied by a weight matrix. So you have the input X, and then you're taking the net input, which is Z, and then you're passing that through an activation function, which will give you H. And then H finally, before going to the output layer, is going to be multiplied by its own weight matrix U transpose. So S is going to be our final output. So this is what happens in the forward propagation. You have your input X, and that's being multiplied, or that's being weighted by the weight matrix W, which would give us WX. And every hidden neuron will have its own bias, and that gets added to WX. So at this point of time at Z, Z is nothing but WX plus B, and that is going through an activation function F. So as discussed, activation function takes a value, and then it outputs another value. And by doing so, it adds some sort of nonlinearity to the model. And then finally, H, which is the output of the first of the hidden layer, is going to be multiplied again by another weight matrix, and it's going to give us the final output, yes. So this is what we had in the forward propagation. Coming to backward propagation, once the output is given, then we have to take the gradients of each of these components so that you can update your weights. So, and again, in the next iteration, you're going to get better results because now when you first started, you're going to start with some sort of randomly initialized weights. At the end of the forward propagation, forward phase and the backward propagation, your weights are going to be updated by a slight margin. And then it is expected that your error is going to decrease in the second iteration than what you had in the first. So this is again another way of understanding what happens with the chain rule. So here, f is the activation function for which z is the input and h is the output. To repeat, z is nothing but wx plus b. The weighted input along with the bias is going to be passed through the activation function, and h is the output which is generated from the activation function. At the time of back propagation, upstream gradient is what you're going to get from the back propagation, and downstream gradient will be the what leaves this activation function towards the next input layer. So what in that here we see that uh, here we can see that the downstream gradient is nothing but the upstream gradient ds by dou s by dou h into dou h by dou z. So this is again what we see in the chain rule. So this is another way of interpreting chain rule. We see that downstream gradient is nothing but local gradient multiplied by upstream gradient. So here we are given an example. If this is the function that we want, so here is a function f equal to ab, and that's what we are going to consider for this. So where a is x plus y, b is the max of y and z, and f is a function of a and b. So we'll start with just to go forward. We are assuming we are taking some values here. X is 1, y equal to 2, and z equal to 0. And we can see here that what we did here is nothing but constructed the same f equal to a and b using some sort of symbols here. So we have x and y here, which are being added. So the output of this is going to be a. As we can see here, a is equal to x plus y, and that's what we are going to get as an output from here. And then we have b, which is max of y and z. So here we can see that we have a max operator for which y and z are the inputs, and the output of this is going to be b. And finally, we're going to multiply a and b together to get f. So that's what the final output is going to be. So here we can see that the different things are shown. So we have a equal to x plus y, and when we are taking the gradients of a with respect to each of its variables, we are going to get 1. That's because if you have a function like function a equal to x plus y, which is nothing but this function is made of 2 variables x and y, and when you're taking the partial derivatives of that function with respect to any one specific variable, you're going to consider the other variable as constant, which is why when you're taking the gradient of a with respect to x, you get 1. And the same thing goes with y. When you're taking the gradients of a with respect to y, you're going to get 1. So this is simple when it comes to a. When it comes to b, what we have here is this function is not as straightforward as x plus y. What we have is we are taking 2 values, y and z, and we are going to return the max value of it. The gradient for this works in this way. So when you're taking the gradient of b with respect to y, if y is greater than z, then the gradient of b with respect to y is going to be 1, or else it's going to be 0. So these are all some of the calculations. What here it is shown what happens when it's back propagated. We'll see this in the example. Yeah, and here this is another example of visualizing what happens in the forward propagation and in the backward propagation. We can see this is how the computational graph is built. We can see that here we have our input X, and here we have the hidden layer, and here we have the output, and the arrows actually indicate the way in which the weight the arrows here again indicate the weights. We can see that there is a color differentiation. The black indicates forward propagation here. So here in this part of the lecture, it's discussed about how different deep learning frameworks like TensorFlow and PyTorch work with differentiation. Though these things take care of getting the gradients and back propagation, it is important that we understand how it all works, so that way you get to know a lot better. So this is some code about the computational graph when you're during your forward propagation and the backward propagation. And so towards the end, I think towards the end of the lecture, there are so many things that were quickly reviewed. Each of these things is actually can take another lecture itself. So here is an article that was mentioned, which is by Karpati. I'm yet to go through this. So the lecture also talks about regularization. So when you have when you're working with language models or word vectors, the number of parameters could be huge. So when that happens, if you're training the model for enough number of epochs, or if you keep training the model for more and more epochs, your training accuracy your training error is going to reduce, and you're going to get very good results when it comes to training accuracy. But if you're also testing it on unseen data, you notice that as you keep increasing the parameters and as you keep training the model for more and more number of epochs, you see that your model is overfitting. So overfitting is where you have the test error, the error at the time of the error on test data is much more than that of the training error. So to avoid that, we can add regularization, which takes care of which tries to prevent overfitting. So vectorization here, it is there are different ways of understand. I think depending on how way you use it, I think you can define vectorization in different ways. But here we are talking about how to make the matrix multiplication much efficient. Here we can see that instead of taking weights and using loops to do all the calculations, if you're concatenating all the weights to form a matrix, and if you're handling everything using matrix, we see that the time taken for the computations is much lesser. Here we see that just for 1,000 loops, it takes around 639 microseconds or something, whereas it is much smaller when it comes when you have tried the same using the concatenation and word matrix. And then we have here different nonlinearities. So sigmoid tanh and hard tanh, these are some of the widely used nonlinear functions before the neural network started adopting ReLU as the more standard activation function. We can see the difference here. Sigmoid takes a value and it produces an output, and the range of this output lies between 0 and 1. Whereas for tanh, it is -1 and 1. The range is between -1 and 1. And we see that hard tanh and tanh are kind of similar, but the advantage with tanh is that it is very easy to compute, where comparing tanh and hard tanh, we can see that we don't have any exponentials here. Just considering the value, if the input value is less than -1, hard tanh is going to output -1. And if the input value is between -1 and 1, it's going to output the number itself. And for any number which is greater than 1, hard tanh is going to output 1. So we can see that ReLU could have been inspired from this hard tanh, because so before we go to ReLU, so this is just one point about tanh. Tanh is nothing but it's a rescaled shifted sigmoid. So if you want to calculate tanh, you can also do that using sigmoid by using this formula, 2 logistic 2z minus 1. And here comes ReLU. So ReLU is where for any value which is lesser, whenever ReLU takes a value and it outputs another value, if the input value is anything below 0, it is going to be 0. The output is going to be 0. For any value greater than 0, the output is going to be the number itself. So we can see that this again is another simple function, but it is doing the job of adding nonlinearity. And it is said that using ReLU makes training much quicker, and also the performance is better because the back propagation gradient calculation all become easier with ReLU. So so when we are training a neural network, unless we are using some pre-trained model, we often start with random weights. So how are we going to initialize those random weights? One thing to do is you can start with all zeros, but the problem with that could be when you're initializing all the weights to zeros, the problem is that whenever you're making any updates, all of the weights start moving in the same direction, or the steps they take might be symmetric and similar. So to avoid that, instead of using zeros as the initial weights, you have to randomize the weights and take some sort of random weights instead of any standard values for all of the weights. So one of the most widely used initialization technique is Avia initialization, where we have so it takes all the weights from some sort of uniform range, and that gives better results. Then we have one slide about optimizers. Optimizers is where you must have heard about stochastic gradient descent and all these things. So you calculate your error, you get the measure of error for the kind of weights that you have started with, and then you have to back propagate those. So the optimizers take care of updating the values and all these things. And so we have some list of optimizers here: AdaGrad, RMS Prop, and it is said that Adam is a good one to use. And these also provide some sort of where every parameter could be optimized differently. So that's where the name adaptive comes from. And coming to learning rates, if you have taken FastAI, you must be familiar with this. Learning rate is when instead of when updating the weights, instead of doing that by the entire margin, you take a learning rate, you multiply your gradients with that, and then you somehow scale down the weight so that make sure that your weight updates don't overshoot. So there are different techniques for this as well. You must be familiar with cyclic learning rates. We use these in FastAI. So this is the quick run through of the slides and what all was discussed in lecture 4. Now I will now walk you all through the blog that I told you I found very useful. So if there are any questions about anything that's discussed so far, please feel free to ask.
One quick question. If you go back up to your slides with the visualizations of the back propagation, right here, this is good.
Which one?
Can you maybe one slide forward where you have the back propagation?
This one?
Right. This is fine. This is good.
Okay.
Could you really quickly explain again the intuition for not doing a back propagation for you? That one's not necessary. Why again?
So you're asking why we're not doing it for you here?
Yeah, I'm just trying to remember what the intuition for not doing it for you was.
Okay, so do you mind if we get back to this once we have gone through the blog, just in case if that clears your doubt?
Sure,
yeah.
No problem.
Sure, yeah, thanks for the question. So let me stop the share and I'll share this. Okay, I hope you all see the blog now. I don't know if any of you have come across this, but this has a very good intuitive explanation of how backpropagation works. So we'll get started with this. So here what we have is a very simple neural network. We have I1 and I2 at the input layer. So we have an input layer with 2 neurons, and then we have and we have one hidden layer, H1 and H2. So this hidden layer again has 2 neurons. And then we have the output layer, which again has 2 neurons. So this, as I said, is a very simple neural network, just to make things clear and easy to understand. So what I would like what I would like to say here is that here we have input layer with 2 neurons and hidden layer with 2 neurons. So we must have heard about weight matrix, like M by N weight matrix or X by Y weight matrix. So what exactly are these dimensions? So to answer that here, what we have here is a 2 by 2 weight matrix, because for every input here, we have, sorry, for every hidden neuron here, we have 2 inputs. So H1 is receiving its inputs from I1 and I2, and H2 is also receiving its inputs from I1 and I2. So if in another case we had 3 neurons here instead of 2 in the hidden layer, then the weight matrix is going to be 2 by 3. So that's how we get the dimensions of the weight matrix. And we have two, we can take that, we have 2 weight matrices here. One is from the input to the hidden layer, and from the hidden layer to the output layer. So this is what we have. So when we say that the model is learning something, the neural network is learning something, all these things with W's are the things that it learns. W1 till W8 and also the biases. What happens here is that W1, W2 till W8, these are all going to start with some sort of random values. And then once you're done with your first forward propagation and you calculate your error and you back propagate it, these are the things that are going to be updated. So these are going to be the parameters of our neural network. Here we have 8 weight parameters. So now let's see, our input value I1 is 0.05 and I2 is 0.10, and the output that it generates is 0.01 and 0.99. So here, for the time being, all the weights W1, W2 till W8 are all randomly initialized. We can see that there are all some random values here. And let's see how the forward propagation works. So what's happening here is that yeah. So we have seen in CS224 slides that here H1 is not going to be any predefined value. We know what the value is going to be for I1 and I2, but H1 is a value which is calculated from the net input. So what happens here is that H1 is going to take I1 and W1, so they're going to be multiplied, and that forms one term of H1. Similarly, H1 also receives its inputs from I2. So I2 and W2 are multiplied, and that forms another term. So we can see that here, the net input for the H1 is going to be the input 1 multiplied by its weight, and input 2 multiplied by its weight, and the bias that is associated with this hidden neuron H1, which is bias B1. So this is going to be the net input for the hidden neuron H1. So we can replace the values as we have given some random values. So what we're going to get is net H1 is some value like 0.3775. Now, this is only one part of H1. What H1 does is it takes the net input and then it uses an activation function to add nonlinearity. So that's what is happening here. So we have the net input H1, which is then passed through an activation function. Here they have used a logistic function, which is the same as a sigmoid function. So what it does is sigmoid is nothing but 1 by 1 plus e power minus x. Here, x, which is the input to this logistic function, is net H1. So we are going to just place that value here, and we are going to get the output. So this will be the output of H1, which is this. So this hidden neuron is going to generate the output 0.593. And the same thing goes for H2 as well. So for H2, what happens is, again, weight one, it has its own different weights. It will have W3, which is this. W3 and W4 are the two weights which are linked with H2. So here, instead of W1 and W2, we'll have W3 and W4. And we'll find the net output for H2, and then we'll find the output of H2 as well, which is like this. So we'll have output of H2, which is 0.59. So now what we have done is we know what H1 contains and what H2 contains. Then we have to go forward to from the hidden layer to the output layer. So as we can see here, even here, we have some set of weights, W5 till W8. Let's see how that works. So for the first output layer O1, the net input is going to be the output from the hidden neuron 1 multiplied by its weight, W5, which is nothing but this. We have W5 here, and we have the output of H1. So these two together are going to form one part of output 1 neuron here. So we are going to calculate that here. We got the net output, and here again we are going to pass it through an activation function, which is again a logistic function. Here we're going to get the output. Now the same thing is repeated for the other output neuron, which is O2. So this is going to receive its inputs from H1 and H2, and it has its own weights, W7 and W8. And we're going to get the output here. Now we have everything that we need. We have the output of O1 and we have the output of O2. The only thing that's left in the forward propagation is to calculate the error. We know the actual outputs here, and we also know the predicted outputs since we already calculated O1 and O2. And now let's calculate the error. So there are different loss functions here. We are going with the simple one, the squared error, where you're going to get the actual value and you're going to subtract that from the predicted value. You're going to square it, and that is going to be repeated for all the output neurons. So here for the for the output 1, we know what the actual value is, and we also know the predicted value. So we are taking the difference and we are going to square it, and then we are going to get the error measure for the first output neuron. And we're going to repeat that for the other neuron as well. So these two put together, it is going to give us the total error, which is 0.29. So when we started with these weights, 0.15, 0.20, and all this is the error that was recorded, 0.29. Now we have the error, which means we have finished our forward propagation. We got the error, and now this has to be back propagated, and all the randomly initialized weights have to be updated accordingly. Now let's see how the backward pass works. So backward propagation is nothing but considering the kind of how well the model has predicted the value, we are going to now update the weights. So what that means is we have E total, which is nothing but the total error. And we now have to figure out how each of these weights are going to impact that error. So, which is nothing but in mathematical terms, we call it this. So the rate, it's the partial derivative of E total with respect to W5 will tell us how W5, how the rate of change of W5 is going to impact the error. So now here comes the chain rule again. So you have E total, and you want to know how the weight parameter W5 is going to impact it. Now, before we go to the equation here, let's focus on this diagram. What we have here, please stop me and ask any questions if this is not clear. I think this is necessary to intuitively understand what exactly is happening here. So this is nothing but the circle here is our output 1, which is this neuron, output 1 neuron. And inside that, we know that it takes the net input from the previous layer, which is for output 1, it is going to get its inputs from H1 and H2 along with their weights, and they are put together and they form the net O1. And then they are passed through an activation function, and that would give you the final output O1. So now what we want to figure out is, how does W5, this weight here, W5, change or impact the total error, E total? So these errors help in understanding how this works. So if we want to know the gradients of E total with respect to W5, we can see that between W5 and E total, we have output O1 and we have net O1. So that's what we're going to do here. So if we want to know how E total is going to change with respect to W5, we should first know how E total is going to change with respect to output O1. And we also know that output O1 is dependent on net O1. That's why we have the gradient here for output O1 with respect to net O1. And then we know that net O1 is dependent on W5. It's also dependent on W6, but since we are only, right now we're only considering W5, and for partial derivatives, we can assume that the other things are constants. So we can say that d net O1 by dou W5. So putting all of these things together, we'll get the partial derivative of E total with respect to W5 is going to be equal to the partial derivative of E total with respect to output O1. We can see here that E total is dependent on output O1, and in return, output O1 is dependent on net O1. We can see that from here, because output O1 is nothing but the output of the logistic regression, output of sigmoid function of which takes net O1 as its input, and net O1 is generated as a result of weighting the input from the weight W5. So that's how this works. I hope this part is clear, because the same thing is going to be repeated for every other weight neurons. So here we are calculating each of these terms. E total, as we have seen in the previous step, is nothing but we have two of them. Output O1 and output O2 are nothing but these two. So to calculate the total error, we should calculate the error that was recorded for this output neuron and the error that was recorded here. So we then combine those two and put them together to get our E total. So that's this equation here. That's this equation here. And now to calculate the partial derivative of E total. So this is the first part. So let's take this part here, the partial derivative of E total with respect to output O1, and let's calculate that. So we can see that okay, yeah. So here we can see that this is what we have for E total, and now we are taking a partial derivative of E total with respect to output O1. So for partial derivatives, as I said, we are only considering the variable output O1, which means any other variable is considered to be a constant. Here, output O2 is considered to be a constant, which means this entire term is going to be 0, which is why we have a 0 here. And let's see what happens with this term. So what we have here is half into, let's treat this entire thing as x. So we know that the derivative of x power n is equal to n into x power n minus 1. So that's what is happening here. So we have this 2 here. So this is x power 2. So which is nothing but 2 into x power n minus 1. So that's why we have that 2 which is here, and then we have 2 power minus 1. So the minus 1 here, the extra minus 1 is here for the internal derivative. We have minus O minus output O1 here, which means that its derivative is minus 1. That's where this minus 1 comes from. And now when we finally solve this, we get this value. So we now calculated the value for this term. Now we have to take care of the other two terms here. So now what we want is the partial derivative of output O1 with respect to the net O1. So to calculate that, we know that output O1 is nothing but a sigmoid function. And the derivative of the partial derivative of the logistical sigmoid function is nothing but the output O1 multiplied by 1 minus output O1. So we are just substituting the values here, as this is already calculated in the previous steps. And we now also have this term here. So now all we have to do is calculate the last term, the partial derivative of net O1 with respect to W5. And for that, we know that the equation for net O1 is this. And so what we're doing is we are getting the partial derivative of net O1 with respect to W5, which means W6 and any other variable is going to be treated as a constant, the same thing as before. So here, the 1 comes from, because when you're taking the partial derivative of W5 with respect to W5, it's going to be 1. So we have 1 here, and out H1 remains so. And here we have W6 term. The entire thing is going to be 0, as W6 is considered a constant when the variable is W5. So this is how you get the output of this partial derivative as well. Now we have everything we need to calculate the partial derivative of E total with respect to the weight W5. We just have to put the values together and calculate it. So now we know how the weight W5 impacts E total. So the partial derivative of E total with respect to W5 is 0.08. We can use this to update W5. So how does that happen? So W5 plus is nothing but it indicates the updated weight. So W5 plus is nothing but it takes the existing or the current W5 value, and then it is going to so this term here, which is the learning rate. So let's ignore the learning rate for a moment here. We have this value that we calculated, the partial derivative of E total with respect to W5, which we just calculated. So, and then we are multiplying that with the learning rate, because as discussed in the beginning, you are going to, you're not going to take the gradients as it is, but we are going to take them by multiplying them with the learning rate, just to avoid overshooting of the weights and updates. So now we have W5 plus, which is the updated weight for W5. This is a value that it is going to use in the next forward propagation step. So 0.35 is the updated W5 value. Let's see what the, so here when we got started, W5 is 0.40. So that's how the weight updates happen. So now we did it for one weight. So we did that for W5. Similarly, we repeat the same for W6, W7, W8. The process is going to be the same. It's just the same things repeated again. So which means we have calculated the gradients, and we have taken care of updating the weights for all the weights that come from that are between hidden layer and the output layer. So this part is done. We still have these weight parameters which are between input layer and the hidden layer. So that again is going to be almost the same, except for just slight changes. So now we can see here we have the whole network diagram. So we have the input layer here, we have the hidden layer here, and we have the output layer here. What we have to find now is how the error is going to change with respect to the weights here, W1, let's say. Now, previously we have taken the output neuron. Output neuron had two parts, which is net output and the activation output. Similarly, even here in the hidden neuron, we have two parts, which is the net input to the hidden neuron and the output of the hidden neuron. So what we're trying to find here again is similar to that of the output neuron. So we are trying to find out the partial derivative of E total, or the error, with respect to weight 1, which would be equal to the partial derivative. So again, let's see what are all in the flow. We have output H1 here, and we have net H1 here. So to calculate how W1 is going to impact E1, let's say EO1, we know that it is going to be impacted even out the net input to the hidden neuron and the output of the hidden neuron are also going to impact that. So that's again the same thing which we did earlier. We're going to get the partial derivative of the error with respect to the output of the hidden neuron, and the output of the hidden neuron is it changes with respect to the net input of the hidden neuron. That's what we have here, the second term. And the net input of the hidden neuron H1 is it changes with respect to weight 1. So this is a chain again, the similar thing that that we did with the output neuron. So now let's calculate each of these terms again, like we did for the output neuron. So to get the first term, E total with respect to output H1, we know that E total is nothing but EO1 plus EO2. As we discussed before, E total comes by summing the error from output neuron 1 and output neuron 2. So since we have two of them, that's what we're doing here. It's simply like we are decomposing E total into EO1 and EO2, since we have two of them here. And now we have to calculate each of these things. It's the same equation here that we have. We're taking it. Let's start with that. Now let's first calculate this part. So the partial derivative of the error at output neuron 1 with respect to the output of the hidden neuron H1. So to do that, we have this equation here, which again is chain rule. We have the partial derivative of EO1 with respect to out H1 is nothing but EO1 with respect to net input. The net input is going to change the output H1. And it's a similar thing which we did, it's similar thing like the output neuron. So we're going to get the values, and we're going to calculate this. And we see that to get the net output of net O1, this is the equation that we had. So when we take the partial derivative of net O1 with respect to output H1, we're going to get W5, because the rest of the things are constant and they are valued to zeros, and we get W5. We plug in all these values and we get this equation, the partial derivative of E1 with respect to the output of the hidden neuron. So that's one part of that's one term which is calculated. And so E1, we have got the partial derivative for E1, and similarly we have to do it for E2 as well, and we get the value. And now we have the total thing for the here we have the partial derivative of E total with respect to the hidden neuron, the first hidden neuron's output, and that's the value. And similarly, we are going to repeat the thing for the other terms as well. I will be sharing this link, and I think if you take a note of each of these things and work on it yourself, I think you are going to understand all of it clearly. So we are going to calculate we have the gradients for all of these weights again, W1 till W4, and here the weights are updated just like the previous weight updates. So all of these weights, updated weights, are taken, and the forward propagation is done again. So now in the first phase, the error that was recorded is 0.2983, whereas once these weights are updated and the forward propagation is done again, the error has it is noticed that the error has come down to 0.10. So it has come down from 0.2983 to 0.2910, at the end of first round or the first iteration. So when you repeat this for number of times, that's how your error and loss function keeps decreasing, and you have to repeat it for as many number of steps as required. So I hope this blog at least helped you to visualize how backpropagation works. I think I'll stop here now to take any questions or any discussions.
Yeah, this is great. So one thing he says, when you update W5,
Yeah.
it says you subtract the where blah, 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 wherever it is. You do a subtraction.
Yes.
But I don't know if there's an intuitive reason to subtract.
Yeah, even I was wondering the same, like what if you have to increase instead of decrease it?
Yeah.
Right?
Right above there, he says to decrease the error, we then subtract this value. But I don't know why decrease the error corresponds to subtraction.
Yeah. So I think it's more like when you start with some random weights, you're going to get a very high error. The loss
Okay.
function is going to give you a very high value. But considering the way the backpropagation works, you're going to try and move in the direction of decreasing loss, right? So
Right.
maybe it got something to do with that.
Okay.
Yeah.
I would add something here. In case we have to increase it, that gradient value will be negative. So
Negative. Yeah, exactly.
become positive
I
and
see.
then increase.
Okay.
So basically, gradient will tell you which way you have to move.
Yeah.
Okay.
So there is a message that in this example, weights and biases are not random. If you're talking about this blog, yes, the weights are random. They were just, I think the author of this blog has taken some random values here and just to show how the forward propagation works and the weight updates work. So there was a question by Christine. So Christine, did this help you with understanding how it works?
I think so. I think the main question I had was in the drawing earlier.
Yeah.
There was back propagation, but not for U. And in that instance, U was at the very end of the function. It was after f of z, and it was multiplied by the hidden layer to get the output. And my question was, why weren't we doing back propagation for U? So this is very clear, and I understand what's happening here, but I'm not sure where U would fit. I understand what H is. H is the hidden layers. I understand the outputs, that's S. I understand the inputs, which is the, I'm assuming that X or even the WX once you get to the hidden layer, but I just wasn't putting together what U was in this whole graphical representation and why we did not do back propagation for U, if that makes any sense.
Yeah, I'm just going through the slides. Just give me a second.
And you don't have to take any time. This was very clear. I think I was just trying to reconcile what U was in the slides and how it fits in here. I'm not sure if that's clear.
Sure. So U must be like f of z is the output of the activation function from the hidden layer. So U must be the weights that we have between the hidden layer and the output layer.
Well, that can't be so because we're actually doing back propagation with weights weights 5, 6, 7, and 8. Right?
Yeah. You mean here in this
Yeah.
example, right? Yeah.
In this example.
Mm-hmm. Yes.
So which part of this example are we not doing back propagation with? Does anybody know? Like which part of this example would you be representative of in the slides?
Okay, so comparing, I mean, when we are drawing some comparison between the slides and this example, the X there is the same as I1 and I2 that we have here, right?
That's right. That's
Yeah,
X.
and then we have capital W, which is nothing but W1 till W4 for the
Yep.
first part.
That's
And then
right.
we're going to multiply that with X, and we have the bias terms here.
Yep.
And then we have there we have H equal to F of Z, right? So that's going to be the output of H1,
Right.
right? And that H, and then we have U transpose into H, right? Which gives us yes. Okay, let me check that. Yeah, so the output of the activation function is H, and then we are taking H and multiplying that with U transpose, which would give us yes. So which means here the output of H1 and H2 are going to be H. Yeah.
Oh, it looks like James is saying U might be the learning rate.
You
Or
might, not really. I don't think
no?
that's the
Okay.
learning rate. Yeah. So if you see in the slides, we have we have H equal to F of Z. F of Z is nothing but the output of the activation function. In this case, it's going to be the output that comes out from H1 and H2. That's right, correct?
Okay. Okay.
Yeah, and then before we get the final output, yes, what we have is we have U transpose into H. H is the output from H1 and H2. And then we have these weights here, which get multiplied with H and finally gives out the output. Output, yes. I don't really think U is the learning rate because it also has a transpose in the slide. So it has to be, I feel it's just another weight matrix.
Can you go back to that slide again?
Yeah, do you want me to open the lecture slides?
Yeah, please.
Yeah, okay, yeah. Yeah. So here we have this. We are starting with X input, right? And we are multiplying that with the weights and then adding bias to it, which would give us Z, this entire thing. We have that here. And Z is going to be passed through F, which is the activation function. The output of F is going to be H, and then H is being multiplied with U, and that's going to give us yes.
If I remember correctly, I think in lecture it has been told that U being the last thing to which after which you get final value of S. So the gradient with respect to U will be 1, so you don't need to exactly calculate it.
Oh yeah, yes. So when you have here S, and when you're taking the gradient of S with respect to S, that's going to be 1. I think Christine is not asking about that. She wants to know what U is here. Is that I feel it must be a weight matrix.
Yeah, it's a weight matrix.
Yeah, it is a weight matrix. I hope, Christian, that clarifies your doubt.
I think I think I need to sit with it a bit, but thank you so much for going through this. This is very helpful.
So it's just, I think
No
it's just a representation, like he's using W, capital W1, then B, then U. You can just use W1, W2, W3 like that.
Yeah, yeah, yeah.
Just for, I think, clarity, and it's really easier to write in the equations and show that this is the final layer.
Yes.
I think that is the purpose.
Yeah. So as in the blog, I think Q represents the weights from W5 till W8. I think that's how it works.
So in terms of updating the weights, we're only concerned with updating 1 through 4.
And 5 to 8, all the weights. So is that part not clear? You have to update all the weights in the network, W1 till W8, all of them. Hello, is anyone talking?
Sorry about that. Yeah, I think I got it now.
Okay, sure.
Another question, if I may.
Sure.
When you do backpropagation, do you do backpropagation for each of the nodes in the output layer, for all of them separately in a particular order?
Okay, so it also depends on how many output nodes you have. So in the example that that was given in the blog, we have 2 output neurons. So let's think about a more simplistic example where you only have 1 output neuron. So in that case,
the question is, say, if you have multiple classes, if it's a single class, then it's easy.
Yes,
because you have a single error. But if you have, say, 4 classes, how do you go about updating the weights? That's with respect to the comments that you were making, that you have to update all the weights. So you have 4 output nodes. You computed 4 errors, right? 1 for each of them. So how do you go about doing backpropagation in those cases?
Yeah, let me share the blog. Just give me a moment. Yeah. So if you see here, we have 2 output neurons here, and output neuron 1 has 2 weights associated with it, which are W5 and W6. Similarly, output neuron 2 has its own weights, W7 and W8. So at the time of updating the weights, all of these weights have to be updated accordingly. So you're going to consider how, so again, just if you take time to go through this blog once again and understand all of these terms, you'll be able to get the way the flow works. So just where is it? Yeah. So here right now we are only considering 1 output neuron, the first output neuron, and we see that to calculate the output neuron has 2 weights, W5 and W6. It doesn't bother about W7 and W8. So it is only concerned about these 2 weights. And the way it works is you have your total error E total, which is given by the error recorded at output neuron 1 and output neuron 2 put together. And what you're going to do is you're going to calculate how EO1 is going to change E total. So for that, yeah, okay, I think I said something wrong here. Yeah. So if you want to update the weight W5 and how it is going to change E total, what you're going to do is just try to get the flow here. You get here the output of the hidden neuron H1 is being multiplied with W5, and you add the bias to it, and that forms net O1 here. The first part of this output neuron is nothing but H1 into W5 plus B2. And then similarly, you do it for the other weight as well, H1 into W6 plus B2. So that's how you get net O1. and net O1 is going to be passed through an activation function, and the output of that is going to form output O1. And now when you want to update W5, you have this equation here, which we discussed in detail. So I'm not really sure if I was able to answer your question.
So basically, I think what you're implying is that if you have multiple classes in the output layer, you go through all of those output classes and update the errors, as opposed to if you have, say, 10 classes, taking only 3 classes and adjusting the weights with respect to the instances where you're making the most errors, and where you don't really make the errors, don't make any adjustments. Does it make sense? So say you have,
I think it does,
you have a
yeah.
classifier that classifies, say, different images or different sentences into a variety of classes. In some cases, you're making a lot of errors. In some cases, you're not making a lot of errors. So I was trying to find out whether you, at every backpropagation step, you go and sweep and update all the weights, even though you're already making pretty good classifications, or there is a little bit of optimization, so to speak. And, just like the way we do the learning, if you take a test, you make a lot of mistakes on particular problems, you try to learn only those problems, because the other ones you're already doing a pretty good job.
Yeah, I can help.
Yeah.
I think I have an answer for that. So you see, so that's a great question. Like, so, okay, say you have 10 classes and 3 classes you're doing really well, right? So you see the chain rule, right? So here, for example, it says the total error divided by the error of that weight, right? So if you are in a particular class where you're doing pretty well, this value is going to be very small. So for that particular weight for associated with the class where you're doing well, you're not going to change that weight a lot. You see. So suppose W5 was the weight that was giving you, that's related to, I think in this example W5 is connected to output 2, right? So suppose you're doing really well on output 2, then delta E total by, is that right? No, no, the error. Okay. So what I was thinking initially is that won't change too much, but but it's not per class the error, right? It's the total error. Okay, sorry, never mind. I thought that would take care of it, but I think.
Right. So for multi-class, in multi-class situation, you're using multi-class log loss, right? So the error is still a single number.
Right,
So
right,
you're
yeah.
summing the error over all the classes.
Okay.
So overall, if if the total error, so your objective is to minimize the total error over all the classes.
Okay.
So I guess if you are making error, doing really well on some classes, but worse, really bad on some other classes, it will still try to, I guess, compromise.
Yeah. Okay.
So
That. Yeah.
basically, if we have a multi-class problem, then the error function will be different from what we have it here. So it will take care of that itself. So as someone was saying, that the error value is a single integer, not integer, sorry, it will be a float. So it is a single value, and when we do the back propagation and we adjust the weights, adjust themselves, so that the overall, that final value is final value is optimized to be like as less as possible.
So there's actually usually it's just a sum over all classes like multi-class log loss, but most packages let you feed like class weights. So you can say some classes are, so for example, if you have extremely unbalanced classes, then you can define different class weights. So when you're training, it will treat each classes differently.
Thanks for the answers. I think that's a good question, and the question also was had something about how do we optimize the gradient update. I think something about that was discussed in the lecture. I'm yet to go deeper into that, but that's one of the things that I would that I have in my list to explore. So maybe once I find something, I'll maybe discuss that in the next study group or post some resources if I come across any. So are there any other questions or anything that you would like to discuss?
Yeah, I wanted to ask if we have discussed assignment 2. I missed last meeting.
Yeah, so last week, Prashant walked through assignment 2. I was not there as well, but yeah, they discussed assignment 2. The video must be available. I think you can go through that.
They have not updated that on.
Oh, okay. Okay, sure. But yeah, lecture, the assignment 2 was discussed.
Okay.
So if there are no further questions, I think we are done for today. We'll be continuing with the next lecture. And if you have anything in specific that you would like to discuss, or if any of you want to present in the upcoming study groups, feel free to update the plan sheet with your names. It would be really nice if more and more people come and take part in presenting. So
yeah, I just want. Sorry.
Yeah. Yeah. Go. No. Go ahead.
So I wanted to ask if people, like anyone has thought about the final project, what they're going to do. If someone can discuss what.
Yeah. So I think we haven't really discussed much about the final projects. I think if anyone has any ideas, or we did discuss, I think like 2 study groups. I mean, 2 sessions before we had a slight discussion about projects. So I have Q&A is one thing that I would be interested in. And also, though it's not totally related, speech recognition is another problem that I'm very interested to work on.
I think I was present in that meeting. So.
Okay. Yeah. So I think after that we didn't really have any discussion on projects.
Okay.
Maybe we can post a message on in the channel and start a thread. If anyone has any project proposals, I think we can discuss it over there.
There is a nice Twitter feed about these projects. Just sharing it on the chat can
sure.
be very useful.
Sure. Can you also post it on the channel?
Yeah, I also post it on Slack.
Sure. Yeah. Thanks, Vikas.
Yeah. Thank you.
So I think if there is nothing else, we are done for today. Thank you all for joining. Happy weekend and see you all next week.